So guys, welcome to the next session, and welcome to all the simulcast locations as well. Thanks for coming here and being with us. This session we're going to talk on the agronomic impact of soil density. And myself, Doug Wiegand, and Will Frank, one of the lead engineers, are going to be doing this session, and kind of sharing some of the research and some of the history and experience that we've had talking and learning about soil density management. So as we think about putting seed in the soil, many times we think through the mechanical and all the different processes, but one of the biggest impacts of how that seed not just germinates, but develops and yields is the density of the soil and how we've managed that soil around that seed. So I'm going to back up just a few years. This is 2008 that this picture was taken. 2008 was the very first year that Precision Planting designed the 2020 seed sense, and we designed a load pin to be able to measure the weight that the gauge wheels were carrying on the row unit. And to my knowledge, I was here at that time, and to my knowledge, there was not that had never been done. We didn't know of anybody on earth that had ever measured the weight carried by that gauge wheel. So, you know, I can remember multiple theories from us at Precision Planting as well as dealers and customers on how much downforce should be applied, right? And how to manage that. And there were even, you know, normally when you get to a group of farmers or a group of us, you got a handful of theories and you even got more opinions, right? And what we learned when we put that load pin on was that most of the theories were wrong and all of the opinions were wrong, right? So it humbled all of us. I can remember engineers telling me how it was so much more variable than what they imagined, okay? And so here's a plot in 2008 where they made a pass on the right side of this flag and they applied 100 pounds of spring weight, applied force. And then they turned around and they made a pass with 400 pounds of spring weight applied to that row unit. You can see in this picture that the 100 pounds did not leave as severe of a footprint as 400 pounds. Now we can come to a couple conclusions right now without even digging this seed. We can probably come to the conclusion that everywhere we look, there's a footprint. And therefore, we achieved depth. Or at least got the disc opener to depth. I don't know if a seed got there, but the disc opener did, right? But which one is right? Well, it depends, right? It depends on how the moisture is. Maybe we needed extra weight to hold moisture, but ultimately, we got to wait a few weeks to figure out which one was right, don't we? If we look at the right side of this, the 100-pound applied force, every plant come out of the ground, or at least it looks that way from this picture. Every plant was identically 1 inch tall, 1 inch spike. It was carbon copy. In the same seed, in the same environment, with the same moisture, and the same temperature, the same soil, 30 inches away, didn't do the same, did it? Some of them came out of the ground. Some of them were 1 inch tall, but there was a whole lot of them missing. Why? What was the difference? It was soil density, wasn't it? So if we zoom in and we take a little closer look on the 100-pound applied force, what else do you notice at this time? What do you notice about that picture? It rained a little bit because it's kind of surface crust, right? And it's starting to dry out and it's cracking. Where's it cracking? On the row? No, it's not cracking on the row. It's cracking 4 to 5 inches on the outside of the row, isn't it? Do you recognize that when you walk in the fields? Do you look for it? Why? That's the question, right? And so if we look at the 400-pound applied force, where's it cracking? Right on the row. The only difference is the applied force. So I decided to do a kind of a test scientific study in my basement. I I went out into my field right there by my house that we farm, and I grabbed a 5-gallon bucket of dirt here a couple months ago, and I laid that dirt out on a table, and I blew a fan on it, and I completely dried it out, bone dry. And then I took that dirt, and on the left-hand side, the left container, left tube there, I just scooped that dirt and I filled it. And on the right side, I filled it about halfway to right there. You can see where it starts to get a little more dense. And then at halfway, I took a little bit of dirt and I put it in the blender, don't tell my wife, and I blended it. And I turned it into a smoothie. And then I put about 1.5 inches of that smoothie dirt that I blended and I ground in above the top of that soil. And then I took and I filled the rest of it. And then to represent a little bit of a field cultivator, soil finisher, disc, whatever you're running, a little tillage, I took a putty knife and I kind of smashed the air pockets out. Didn't compact it because it was bone dry. And then I put water in the bottom of that pan and I put it on time-lapse video and I said, how's this going to work? And you can see that water wicking up through that soil. On the left-hand side, it's going pretty good lick. On the right-hand side, it kind of hit something and it's not moving through it. And I left it in there for a week. It's amazing how 5 days can get shrunk into 28 seconds. That's incredible, isn't it? But at this point in time, I said, okay, now my left-hand side is pretty well saturated. My right-hand side, well, it's part of the way. And what'd the top look like? That's what it looked like. Well, that's the same soil, came off the top 4 inches of the same spot in the field. It's soil density management, isn't it? When we change that, it affects everything. It affects air movement, water movement, microbial activity, root growth, plant growth, germination, emergence, the whole works. And so optimum emergence requires soil density management. You can just write that down. It won't ever change. It's the way God made it. So as we look at the way it was on our farm, this was the first year as well in 2008 that on the Wiegand farm that I help out on and grew up on, that we put a load pin on the Kinsey planter that we run. And I was in the tractor here with Uncle Mark. He was driving, I was a buddy seat. And we came to the conclusion that we needed to run our spring applied pressure in the 3rd notch. Because if we backed it off to notch number 2, we learned that we lost weight. We weren't leaving footprints anymore at some spots throughout that pass. So we went to notch 3 and we planted the whole field. And when I look at this, it makes me realize that there's spots within every pass that I was carrying 200 to 300 pounds of excess weight. And there were spots in every pass that I was carrying just about the right amount. As we look at that same picture that had some on the 400-pound that was exactly 1 inch tall and most of them on the 100-inch was 1 inch tall. At V6 to V7, there was a 10-inch height difference. Well, that wasn't due to germination, and it wasn't due to emergence, at least to some of them. Why is there a 10-inch height difference? Air movement, water movement, availability, microbial activity, there's a big difference. Most of us in the farming industry, we grow up and we become, I would say the farming industry is probably the most mechanically inclined industry of anything out there. Why is that? I got a couple theories. You know how it is. We all got theories, even opinions, right? I think the reason we're so mechanically inclined is because from a very young age, we're very good at breaking things. And I think the other reason why we're mechanically inclined is because we're so tight, we're not willing to pay somebody else to fix it. So we learn how to fix what we break. And then we break it again, and we do it over and over and over again. So as we take our planters out of the shop, out of the cold shed, and we bring it into the shop, and we're going to go through it here in the next few months, we're thinking mechanically, because that's who we are, right? And we're going to say, man, I got to get all the wear parts in here. I got to make sure everything's calibrated right so that way we can get good seeding depth and gauge wheels are working right. We're going to firm the sidewall. We got to make sure the Keaton seed firmer is ready to go. And we got to make sure that closing wheel is lined up and centered and the right gap. And we're thinking mechanically, right? What's the soil thinking? Well, the soil's saying, hey, when you come through with that sidewall, or when you come through with that disc openers, you're going to blow this dirt up on each side. And you're going to create excess air. And I want you to firm that back down to where we don't have excess air. Because if you have excess air, you're going to increase evaporation. I'm going to lose moisture. And then it's going to say, hey, this seed is going to say, you know, I got this air pocket underneath me that if you don't press me down to the bottom of this furrow and get good seed to soil contact, I'm not going to imbibe water as quick as my neighbor. And I'm going to slow down on my germination process. And the closing wheel, the seed is saying, hey, you just came through with 2 discs and you forced a trench open in the soil. And therefore, you created a little bit of compaction on the sidewalls. And I'm going to send some roots out that I need to get out to the bounty that soil can provide. So I need you to get rid of these sidewalls so that I can stretch my arms a little bit, right? And what are we talking about? We're talking about soil density management. So if you read the agronomy articles and manuals and books, what you'll do, you won't have to go very far and you'll find a pie chart that looks just like this. And I've seen some pie charts that label this, above it it'll say healthy soil. You think, well, what's healthy soil mean, right? And some of them, I saw one of them that labeled it the ideal composition of soil, right? And so if we look at that, what they call healthy soil would be half of that soil profile is made up of solid. And that solid is made up of sand, silt, clay, and organic matter. And the other half of that profile is made up of pore space. And that pore space is made up of air and water. And ideally, if we can hit 50% and then half of that pore space is air, half of it's water, we're going to hit healthy soil. That we're going to have optimal germination. We're going to have optimal root growth. We're going to hit optimal microbial activity. And ultimately, you're going to hit your optimal yield. So, you know, the one thing that kind of throws a curveball into a lot of us as I was growing up is the microbials, because I can't see them microbes. They're pretty small. And so how do we make sense of that, right? So I was doing some research, and about a year ago I ran across this study that talked about, and they did a scientific study that connected the relationship of water-filled pore space to the soil microbial activity. And so you can see that when you hit about 50 to 60% of that pore space is filled with water, that you're going to increase microbial activity to maximum amount of monification and respiration. That's a good thing, isn't it? Because that's going to crank nutrients. That's also going to be where you maximize nitrification. Nitrification is where we're going to take and convert, the microbes are going to convert ammonium to nitrate. That nitrate, ammonium will stick still. Nitrate will start to move in that profile towards the roots with the water. And if we get above 60% of that pore space filled with water, you start to introduce denitrification. Denitrification is where you saturate the soil, you drive the oxygen out of the soil, the anaerobic bacteria start to convert that into gas. And they gas it off the field, right? So that's not a good thing. So there's the connectivity as we think through, why does soil density matter? So let's back up. Let's break it into 2 parts. The first thing we got is germination. What do we have to germinate a seed? Water, air, and temperature. If I'm missing any one of these 3, you flat out will not germinate a seed. If I can have adequate amounts, you're going to have speed of germination. And more importantly, you're going to have consistency of germination. The other side of that equation is microbial activity. So when I can hit the right soil density management, I'm going to increase my nutrient availability and my nutrient supply. I'm going to increase the plant and the root growth, and ultimately, I'm going to increase yield. So now we've talked through the mechanics, we've talked through the agronomics. Let's connect to the dots. Now let's look back at that row unit. Let's start thinking like an agronomist, not just a mechanic. On this planter, there's 4 things that are going to require weight to do the job that we want to do, plus address soil density management. Above this planter is weight that's going to be applied for that. Hopefully, we have enough weight left over that we hit just the right amount of sidewall downforce, because that's where it's going to be carried on that gauge wheel to accomplish the task at hand. So I'm going to turn it over to Will Frank, and he's going to share with you guys some research that he's done here at Precision as well as on his own farm.
Thanks, Doug. So my family farms about 12 miles west of Precision Planting. You can see here we got a Kinsey 3600 planter, 16 row. So we do vertical tillage on our farm, run an inline ripper in the fall and a Great Plains turbo chopper in the springtime just ahead of planting. So in general, we have pretty light, pretty mellow soil to plant into. For years, we ran 4 heavy-duty downforce springs in the 4th notch. So if I look at Kinsey's owner's manual, they're telling me I was applying 470 pounds of applied downforce. Now that we run Delta Force on our planter, most of our maps look like this one on the right. So we haven't changed our tillage practices, and you can see the applied downforce map tells me there were many times I was putting little to no additional downforce on our row units at all. So that tells me for years I was running 400 pounds or more extra down pressure that I didn't need, but I didn't know because I didn't have a load sensor. But I knew I didn't want to plant shallow, right? I knew that would hurt me. So this morning you guys heard Jason Webster talk about how important automated downforce control is on our planters. And this is why. This is our goal, right? We want all of our crops to emerge and be this consistent. So if you guys haven't done so before, or even if you have, I challenge you this year on your farm, go out to your field and step off 1/1000th of an acre. Count the number of live plants you have there, and then look how consistent those are. If you find corn plants that are 1 leaf collar behind, classify those as a late emerger 1, or LE1. But if you find corn plants like this one that are 2 leaf collars behind, you need to classify that as a LE2. So that corn plant, that seed, it had the same yield potential as all of its neighbors when it was in the bag. Something went wrong. The soil density around that seed was not optimized like it was next to its neighbors, causing that plant to emerge late. And now that little guy is going to struggle its entire life. So as we advance in the growing season, look how much smaller this stalk diameter is compared to this plant that emerged on time. So those neighboring plants got a quicker start out of the gate, and they were able to overgrow and shadow that late emerger too. So sunlight warms the plant and causes it to perspire. So corn plants sweat just like you and I do to stay cool. And when that happens, that corn plant uses its roots to draw more water into the plant, and with that comes nutrients. The plant then converts those nutrients into starch, and that starch gets packed into the ear to generate yield. But through the years that we've been looking at this, we've seen that if a corn plant is 1 leaf collar behind, the size of that ear is going to be about half the size of an average size ear. If that corn plant is 2 leaf collars behind, it won't put on a harvestable ear at all. So in our stand count, if we have 30,000 live plants, but we only have 29,000 harvestable ears, that's a 7 bushel per acre hit in yield. But emergence is only part of the story. You see at V4, that corn plant is transitioning from the seedling roots to the crown roots. And it's those crown roots that for the first time they're trying to expand through the furrow to find all that water and nutrients. And if they get stressed because that sidewall is compacted, they're going to pull back the yield potential on that corn plant. And when that happens, it's going to reduce the number of rows around on that cob. So if we reduce those numbers of rows around from 18 to 16, that's a 24 bushel per acre hit. So we can minimize these soil density errors by putting load cells on our planter. Our load cells take readings 200 times a second, and we display those values on the 2020 so that you have real-time feedback from the cab of what's happening back on your planter. We can then put hydraulic cylinders on every single row and automatically adjust to maintain just the right amount of weight on our gauge wheel. So here's a video of Delta Force actually running in the field. So that hydraulic cylinder there, that cylinder can remove up to 450 pounds from the row unit and transfer that weight to the bar, or we can utilize that frame weight and transfer up to 650 pounds to the row unit. So if we have heavy bottom ground and a light sandhill all in the same pass, we can handle that, right? We can adjust as we go. So this is what it looks like to run Delta Force on our planters. So on the left, this is a downforce map. So this is the net result of the weight on our gauge wheels. This is what the load sensor is measuring. And you can see it's pretty consistent. It's about 100 pounds of weight on that gauge wheel for the entire field. But over on the right, this is the applied downforce map. So this is just how much Delta Force needed to adapt as it went through the field to maintain that 100 pounds. So as we look in the north, this is a strip till area of the field. And a lot of that area of the field is pink, indicating that, again, Delta Force was removing weight from the row unit and transferring it to the planter. But if we look at the south part of the field, it's an entirely different story. Here there were areas where Delta Force needed to apply up to 300 pounds of weight to maintain that 100 pounds on the gauge wheels. And why was that? So this was a high residue area of the farm. This planter has row cleaners, and the grower controls those row cleaners with a product called Clean Sweep. And so lots of residue here. He wanted to use those row cleaners to push that residue out in front of the opening disc, so he didn't hairpin that residue. So when he did that, he cranked up the pressure on those Clean Sweep cylinders. And remember the image that Doug showed you. Those row cleaners take a certain amount of force to get in the ground, and we just increased it. So that's why Delta Force needed to apply that additional 300 pounds to maintain that 100 pounds of weight on the gauge wheels. So Beck's Practical Farming Research, they do agronomic studies every year on many different topics. They've done downforce studies with Delta Force for years and have always showed very strong results. So here's data from 2019 across their 4 different sites. And you can see on average, Delta Force running in automatic mode had a 2 to 7 bushel advantage as an average across their 4 different sites. So I think the question that we need to ask ourselves if we're not running Delta Force on our planter is what percentage of time did you fall into each one of those categories? How much yield did we miss out on because we didn't have automated downforce control? But our research goes well beyond corn. So this picture, you can see Tanner here in the green shirt. He's working with Joshua and David, and they're painting popsicle sticks so that we can do flag tests in soybeans. So for just over 10 days, we went back to this field, and we put different colored popsicle sticks next to those soybean plants that emerged in the last 24 hours. So with this, we can get an overall stand count for the field, but we can also track those individual days of emergence all the way through the growing season and learn how emergence affected that plant. So here's a downforce trial that we did in 2018. So here we were no-tilling soybeans into standing corn stalks. This was a relatively heavy clay field, relatively dry. So you can see we ran 3 different downforce levels, and we had 140,000 plants per acre as our target pop for all of those different treatments. And you can see where we went low on downforce, it really cost us in our stand count. We had 44,000 more soybeans emerged in the medium downforce setting than the low. And why was that? So we got those seeds to depth in the low downforce area, and they were in moisture when we planted them, but we didn't firm that sod well enough to maintain that moisture around the seed, and therefore they couldn't germinate. So we had 39% fewer soybeans emerged in that low downforce area. But fast forward to 2019. This was an entirely different year for most of us in the US. So this video was taken just 10 miles west of precision planting on June 2nd. So in the average year, on June 2nd, Illinois has 91% of the corn and soybean crop planted. But last year, we only had 33% of the crop planted. And one day after this train engineer, he's worried if he's going to make it through this standing water. My family's trying to plant soybeans just a mile and a half north of there. And you guys can see conditions were less than ideal, right? But hey, it's June 3rd. I got to get something planted, or I seriously have to think about taking preventive plant. And unfortunately for me, I got stuck on the first pass in this field. Not exactly how you want to start the day, right? So I tried to rock out of this for a few moments, and ultimately I had to call Dad. He came down with a Magnum and pulled me out. So I was probably only shut down for an hour, but I probably set the soil density in that spot back 15 years. So 2018, 2019, two very different years, right? Here's a downforce study that we did in 19. Again, 3 different downforce targets. You can see we upped the population to 160,000. We were a little bit later this year, right? And as I look at the stand count, where I went high on downforce, it really cost me. I had 38,000 fewer soybeans in the high downforce area compared to the low. So why was that? The 2018 field was limited on water, right? The 2019 field was limited on air. And so if I went high on my downforce setting, I squeezed out any little remaining air that was in that soil structure, and I made it so tight that those soybeans just could not emerge in that environment. And 33% of them just rotted in the field. So as we follow that crop through the growing season, this is a picture from July 31st. You can see Tanner from our agronomy team. He's out there, he's pulling plants, and he's looking at roots from the heavy and the light downforce settings. And roots are lazy, right? They want to grow to path of least resistance. And you can see this is a plant that we pulled from the heavy downforce setting. This root came down and it hit hard pan, didn't it? And it grew to the side until it found soft enough ground that it can continue growing downwards. Not exactly what we want to see, right? So fast forward to harvest time. So harvest time is always my favorite time of the year. And this one was a special one for me. You can see this is a picture of my son Noah. He's just under 2 at the time. And this was his first opportunity to jump in the combine with me as we harvested this plot. And as we look at the yield results, the yield really followed the stand count. Where I went high on downforce and squeezed out all that little bit of air, it cost us in yield. We had a 3.8 bushel hit. So Beck's PFR, they also do downforce studies in soybeans. And you can see they show up to a 3 bushel advantage to running Delta Force and automatic control. So let's back up just a moment before Noah and I harvested that downforce plot. Remember I told you I put flags out in those soybeans, right? So I went back to each one of those flags and I pulled plants from each day of emergence. And then I counted the soybean pods on each one of those plants. And so we've done that for 2 years now. So the graph on the right, this is data from 2018 and 19, and the numbers in red are the average between the 2 years. So I broke these plants into 3 different groups. I called the soybeans that emerged within the first 3 days on-time emergers. And the soybeans that emerged 4 to 7 days later were LE1s, or moderately late plants. The soybeans that emerged 8 days or later, those were severely late plants. So if my soybeans emerged 4 to 7 days later, I had 30% fewer pods on those plants compared to the on-time emergers. And if they were 8 days or later, I had 68% fewer pods. And you can see this in the pictures, right? Here's plants from the on-time emergers compared to the severely late. Quite a few more pods over here on the on-time, right? So I think for years, a lot of us have thought if we don't have the desired stand count on our soybeans, we can just head back out with the planter or drill, and we can add some more soybeans, right? But if you guys went to Corn College in 2018, Isaac and Ken Ferry, they put this to the test. They put in a plot where they planted 80,000 soybeans. They let them emerge to the V2 growth stage, and then they went back out with the planter again and planted another 80,000. And Isaac's picture here shows the results. So here's the original stand of the first planting. Good pod set, right? And this plant's ready to harvest. If I look at the second planting, we have maybe 5 pods on that plant, and it's not ready to harvest, right? So Isaac's picture and their research is confirming my research, right? All of our yield is coming from those soybeans that emerge first. So it shows us the value of automated downforce control in soybeans. So I'll ask you guys a question. What crops don't respond to soil density management? I believe they all do, and not just row crops, but cereals and specialty crops as well. So that's why 2 years ago, we took proven technology from the planter and applied it to air seeders with a product called Cedar Force. So we developed a new load sensor to measure the weight on those gauge wheels and came up with new ways to automatically adjust the down pressure on drills. And Cedar Force comes in 2 options. The first is Cedar Force section that you can see here. We have a hydraulic manifold, and we put 1 at each rock shaft cylinder so that we can independently control the pressure in that rock shaft cylinder by sections. So rather than having 1 static pressure across our entire drill, we can break that up into sections and sense and adjust as conditions change. So good downforce is a term that's defined by having between 0 and 200 pounds of weight on our gauge wheels. And so our plot research has shown that as we increase that percentage that we're in that good downforce window, yield in wheat goes up as well. So we had an air seeder, a grower that we were working with, and we put load cells on his air drill, and we said, set your down pressure where you normally would set it and plant your field. And we found that his drill only had about 75% good downforce. But Cedar Force section can get us to 95%, and Cedar Force row by row can increase that all the way to 99% of the time. So that's delta force level performance for our drills. So Phil Needham of Needham Ag Technologies out of Kentucky, he's an agronomist that really just focuses on wheat. Phil has 2 1560 box drills, and they're 1 serial number apart. They have the exact same setup for plots, except one of them has something a little different. One has Cedar Force row by row. So with this, Phil uses these drills to put in downforce trials, and he's seen a 30% increase in stand count when using Cedar Force row by row, and a 4 bushel increase in yield. So Phil, as an agronomist, I mean, his growers are paying him to take them to the next level, right? And Phil's really excited about the opportunity that this can offer his growers. But as we branch out and study other crops, we don't just look in North America. We've really studied crops across the globe. So here's a video I took in France. This is one of our engineers, and he's planting sugar beets in a Fendt tractor and a monosem planter. So Alexi let these soybeans emerge, and then he went back with a research tool called a pogo stick, and he measured the spacing performance of those sugar beets. So you can see a picture of our pogo stick there on the right. It's a tape measure that has a built-in encoder so that we can measure the spacing between each plant and record that data on an iPad. We can identify skips and doubles that are metering errors, and we can calculate spacing metrics like SRI, which stands for Seed Release Index. So the first thing we do to calculate Seed Release Index is those skips and doubles we identified, we remove those because those are metering errors, right? We just want to look at spacing. So then we look at the standard deviation between the plants and divide it by the average spacing of those beets to get SRI. So with SRI, the lower the number, the better. So if I have an SRI of about 20 when I'm planting, I feel pretty comfortable with that. But the SRI on these beets was 15, so that's excellent, right? But through our trials, we've really been able to show just how the crown diameter and the weight really varies depending on emergence. So look at these beets here next to this green flag compared to these next to the red. These have twice the crown diameter and the weight as those next to the red. So we've always had to set the defoliator for the average beet size, but that gets really tough when we have this much variation. So if we can help promote more even crown height, we're going to have less damage and less foliage in our piles. We can also better set up the harvester for wet or dry conditions when we're fine-tuning those pinch points to lift those beets out of the ground and fine-tune those grab rollers for more even crop flow through the harvester. We can reduce slicing and fall through as well due to a more even-sized beet due to more even emergence. So I think it's fair to say that even emergence even matters in sugar beets. Okay, so as you look at this photo again, so now we understand downforce management, right? We've planted our seeds, we've got them to the proper depth, we've managed the weight on our gauge wheels to firm those sidewalls just enough, and we've firmed that seed with the Keaton seed firmer. But there's still one very important job that that planter needs to do. We need to close this furrow. So let's back up to 2012, when our closing research at Precision Planting really took off. So here you see a picture of an 8-row John Deere research planter that we had at the time, set up with multiple different closing wheels. Notice all the GoPro cameras that we have at the top there? We were trying to record and study the closing action of each one of these setups. So this got us started in central Illinois, but we knew we needed to get to different ground conditions. So in 2012 and 2013, we had a 12-row research planter that we took to 16 different sites. Every year we started in the south in February and we moved to the north as the planting season progressed. So we experienced raised beds in Louisiana, sticky clay in Kentucky, terraces in western Iowa, and even the Red River Valley in North Dakota. And we did a lot of digging. So there were times we had 6 or 8 engineers behind the planter just digging seed and evaluating closing performance. We looked at so many closing wheel options that we needed to break them into different categories. So we looked at wheels, lightweight wheels like dual rubbers on most of our planters. We looked at heavyweight wheels like cast iron. We looked at mild spikes. And mild spikes, I would classify those as ones that have integrated depth bands, limiting the distance that they can penetrate the ground. We looked at aggressive spikes and also some disc closing systems as well. And so for each of these, we ran them at different closing forces, just to learn strengths and weaknesses of each of them and how they responded to these different conditions. We even looked at closing wheel spacing, and what we found was if our closing wheels were set too narrow, we could close the top of the seed trench and think we were closed. But if we looked around that seed, we could find an air pocket. And if we set that closing wheel spacing too wide, we would close at the bottom of the seed trench, but we'd leave an air slot to the top of the surface. And we had a goal in mind. We wanted to achieve 96% ear count potential. So thinking back to our stand example, we have 30,000 live plants, and we have 29,000 harvestable ears. That would be 96% ear count potential. So here are the results from the dry seedbed conditions. So here, it was common we had dry soil on top of our fields, and so the least aggressive wheels did the best, the rubber wheels. The aggressive spikes did the worst. And why was this? The more aggressive we got, the more dry dirt we knocked in on top of the seed. And then as we go to tough seedbed conditions, these were soils that required more closing force and had more moisture. You can see the opposite is true. The rubber wheels, which in the dry conditions did the best, they're now doing the worst, and the most aggressive are doing the best. But it wasn't until we moved to the ideal seedbed conditions that we were able to achieve our goal of 96% ear count potential. So out of all this closing research, we came away with 3 goals for closing. The first one is we wanted to firm that seed and have good seed-to-soil contact, but leave no slotting or air gaps. We needed to leave a mellow path to the surface for even emergence. And then number 3, we needed to retain moisture around that seed, especially in loose seed environments. So as we think back to the research I just showed you and all those different systems, think about how often we're planting into ideal conditions. Did you guys ever have ideal conditions in 2019? I did not on my farm, I can tell you that. So we recognize that as a problem. That's why we set out to develop a system that worked well in all planting conditions. And we landed on a product called Force. So Jason Webster this morning, he talked about the great results that he's seen at the PTI farm with Force. But let's dive in a little bit more and understand exactly how Force works. So Force is an automated 2-stage closing system with integrated sensing. So the first stage is our notch wheels. And they're set pretty aggressively so that the bottom, or the closest point between those notch wheels is at the bottom. So we've seen with 2-stage closing systems, it's still important to close from the bottom of the seed trench up. The second stage are our stitch wheels. So those have some closing action to them as well, but they also act like a gauge wheel for the first stage notch wheels. They limit the depth that the notch wheels can penetrate the soil. So it sounds a lot like our gauge wheels for our opening disc, right? So just like putting a load cell to enable delta force control, we added a load cell on our second stage so that we could measure the amount of weight on our closing system and then automatically adjust in a row-by-row fashion with our closing control module. So as we were developing Force, we really wanted something to be able to move that development along faster. We needed a tool to be able to tell us where to dig in the soil to evaluate that performance. So we came up with a research tool called PaintJet. So you can see Force here, this is it in the green. We're on a John Deere planter here, and PaintJet is this gray contraption coming off the back. So PaintJet works with the Force closing sensor by sitting on our planter can network. So when the closing sensor measures that we don't have enough weight to close properly, a message is sent to the PaintJet module to make a mark on the ground so that we know exactly where we lost closing. So then here you can see John, he stopped the planter, hopped out of the cab, he went back to that exact same spot, and he's able to dig and evaluate for himself how we closed. And you can see, sure enough, we left an open slot in the dirt there. So running Force on our planters is just like running Delta Force. We really have 2 main metrics that we're paying attention to. The first is closing margin. And this tells us the amount of extra weight that we're carrying on our closing system. The second is ground contact percentage. So this tells us the percentage of time that we're carrying weight on our closing system and we're able to close. We have 2 maps as well, one closing margin and then the applied closing map that just show you how often Force needs to adjust as we go through the field. So this is fun to talk about, but I want to show you guys how Force and PaintJet work. So we built a track here, and on the screen you'll see a graphical representation of that track. So on this side of the track we have soft soil, hard soil in the center, and soft soil again at the end. And so we built this track just with plywood, and we left trenches. And we used foam baseballs and basketballs and put them in the trench for the soft soil. And we used rubber hose to simulate the hard soil. And then we covered it all with plastic to have a nice smooth surface to plant across. So we're going to run across this track with our 2-row planter. So our first row is in static mode. It has a load sensor installed, but it is not going to automatically adjust as we transition through this field. Row 2 is in auto mode. So it's going to sense and adjust and able to maintain our closing margin. So as John takes off here, we'll switch to a GoPro camera behind the planter so you guys can see paint jet working. So at the top of the screen here, you'll see 2 pressure gauges as well. So this one on the left, this is the pressure we have in row 1's closing bag. The pressure gauge on row 2 is shown here on the right. And so watch row 2 as we transition from that soft to hard soil. You'll see that pressure automatically increase. So John takes off here. So we're still in the soft soil zone here. And whoop, right there we changed, right? Row 2, the airbag pressure really increased compared to 1, and paint jet is now painting on the ground, right? Indicating that row 1 is losing closing performance. And as we get to the end here, transition back to the soft ground again, now you see row 2, that pressure has dropped a little bit, and paint jet stopped, indicating row 1 had enough closing pressure to close that seed trench, right? So switching back here, this is another view of it, but this time let's watch closing margin. So this is how much weight we have on our closing sensor. So row 1, it starts out at about 20 pounds, and row 2 is at 30. But as I play this video and paint jet starts to fire off, notice row 1, the closing margin fell to 0. That's why paint jet is painting, right? We're losing closing performance at that point. Row 2 is able to maintain margin. And when we get back to that soft zone, you'll see the closing margin on row 1 come back up to about that 20-pound mark. So paint jet, it's been a great research tool, allow us to progress through furrow force development faster, but hopefully that shows you guys the value of automated closing as well. So I'm going to turn it back over to Doug. Doug is going to share with you some things that we've learned in the beta. Thanks, Doug.
Thanks, Will. So let's back up to the spring of 19 for the Furrow Force beta. We all saw this on May 26th. The report came out here. Euro and American model solutions over the next 2 weeks continue to indicate we have virtually no window for plant 19. And that's pretty well the way the season went, didn't it? Trying to get in the field. We got in the field and finished up in June on our farm. So we were able to get in the field after this in 2 weeks, but it was tough. It was a late year. So it was the most challenging planting season in decades, really. And in my years at Precision Planting, a little over 16 years, it was definitely the most widespread. So every year there's pockets of dry and wet throughout the North America. This year it seemed to be a few pockets that weren't wet, but most of them were. So it was our longest spring beta planting season ever. It was 18 weeks long from the time the very first planter started in the southern U.S. to the last planter getting seed in the field. Because it was 18 weeks, it allowed our engineers and agronomy team on the R&D side to do lots of improvement designs and validations in the field while planters were still running. So here's how it looked, the scope of the Furrow Force beta. There were 715 rows. There were 55 planters within 20 states. We were on all common U.S. planter makes. The conditions that we went into were pretty much about everything. The conventional till, strip till, no-till, cover crops, rocks. Some people would say, is rocks a condition? Trust me, some areas rocks is a condition, right? And we had to add one this year that's normally not in the agronomy manual, and it was entirely unfit conditions, okay? So how that looked when we look at the map is 55 planters across the U.S. ran the Furrow Force beta. The bulk of those planters, what we did is we had them set up half of their planter with Furrow Force, and the other half of their planter they ran with their existing closing system. So, you know, if that's the case, then that would have been their closing system of choice for their conditions their environment. I'll back up there. The Agronomic Testing Circle, the shades, is basically where our R&D team, the engineering and agronomy team with the R&D here at Precision Planting, we're able to get onto planters and do additional agronomic testing in addition to just the mechanical applications. So here's a planter in western Iowa. You can see he's planting no-till. They have a few hills out there, western Iowa. And so they plant in no-till, and in no-till you can plant as the rain's coming a little bit longer than you would be able in tillage, right? And so you can see this guy's planting, and it's actually raining there right now while he's planting, but you know, I had somebody call me this spring, and they said, hey, my Downforce or something, I forget what it was, wasn't working. And I said, well, after talking with him a while, I realized his system was pretty wet. I said, well, did it get rained on? He said, yeah, it got soaked. And I said, boy, you ever drop a hairdryer in the water and see if it works? Normally doesn't, right? So it was challenging. It's challenging when we have to be planting in the rain and the water and with electronics and everything else we're doing. So here, when we started with the wheel on the top of this pitcher, and throughout the season there was a lot of different iterations that we designed for different challenges that we ran into. For example, that top wheel, who would have known it's just the right gap between the teeth that a corn stalk will just fit snugly right in there, and it will hold on to that corn stalk until you need it, right? And it doesn't let go of it. And so by simple things like just widening that gap, lessening the number of teeth on that wheel, made huge improvements, immediately solved some of those original first challenges that we had. And here we even employed some farmer engineers. This is Gary Mulbauer out in western Iowa in his shop doing some grinding on that first stage disc wheel that we have. And then because it was long, we were able to get these design changes. And then one of the challenges that we had were the second stage stitch wheels, when we would go into wet or muddy conditions, would tend to ball up with mud either on the inside, the outside, and then it would just start to push instead of roll. That's what happens when you get on a greased surface, right? So the engineers went to the shop, they made some scrapers, they put them on here, and they challenged it. So here's a video of running in, I would say, muddy conditions. You know, and as you look at the first stage wheel and the second stage wheels, the stitch wheels, they seem to be doing a pretty good job there. I don't know, maybe they should try a little muddier, but not a lot of buildup. The scraper must be, transport tire, not so well, right? Okay, so all you have to do is not build up prior to the transport tire, and you're good, right? The guy's going to stop at that point. So the next thing is, it went into this condition. This is more of an ideal condition where conventional tillage, it was a high amount of residue in this along with a number of clods on top, but moisture-wise, it was about right. So we look at this, and as we analyze the furrow force in the field, as many of the beta growers did, when you got to where things were working and the right set of wheels and redesigns were done, it did a great job of pinching and eliminating that sidewall above the seed, and that stitch wheel really doing a good job of firming that down to the right tension. As a matter of fact, probably the most common phrase that we heard from growers that ran furrow force in the beta this spring was, I can't find the furrow. Yeah, think about that. I mean, since you're a young boy, or at least I'll talk about myself, since I'm a young boy, if Dad said, go see if I can dig seed, what would I look for? What's the first thing I looked for? The furrow. Yeah, and once you found the furrow, well, then you just dug right on down like a chipmunk and you found seed after seed after seed. What if you couldn't find the furrow? We've created a challenge here, right? So as we can't find the furrow, here's a picture in Iowa that a guy planted corn into corn stalks, and if I look at this, it looks like there's plenty of moisture, but where's the furrow? It's hard to see, isn't it? Doesn't look like there's any evidence. And here's a picture from northern Indiana of a guy planting corn into soybean stubble. Same thing. And then here's a picture of a guy in North Dakota planting corn in behind wheat stubble. And you can see North Dakota is the only one at that time that had dry dirt, right? There's some dry dirt in there, and North Dakota actually got things in the field prior to we did in the Midwest. They got done, so which is great for them. I know there's many years they have additional challenges. So not only did we see that we got the seed in there and not a lot of evidence of a furrow, but the other thing I noticed with this picture is we see when we're digging behind furrow force is there good moisture? Did that first stage disc opener do a good job, or disc closer do a good job of closing that furrow from the bottom up? We don't want to knock any dry dirt in there around that seed, or we're going to take it away from the density management we're after. Here's another field that the engineers went out and they ran with automatic furrow force across the whole planter, and they at first ran manual, or for a segment there ran manual. So you look on the left-hand side of that map and it shows the manual applied force. It was a static amount of air pressure in the airbag. It didn't vary it. And then on the right-hand side where the closing margin map is, that tells us the result every 1/5 of a second of what the gauge wheel was carrying in leftover weight or closing margin. So there's quite a bit of blue in there. And so then they turned on the automatic control. And when they did that, they noticed that within every pass, that automatic controller was adding and removing weight. There's segments of the time it had the same amount of weight as what the manual was. But there's segments of the time it had more and it had less in order to maintain that margin target that we were after with those closing second stage stitch wheels. Here's another operation that we ran just south of here, a farmer that we work with on the R&D side, and they ran half a planter of furrow force manual and the other half was furrow force automatic. So the combination of the two, they went out and they planted, and you see here the DeKalb 5830 in the automatic mode made 207.8 bushel. In the manual mode, it made 198 bushels. So I asked Aaron, one of the agronomists, I said, what's the farm average here, or the field average? And he said it was 9.8 bushel. I said, okay, well, man, that's pretty good. How about the farm average? If did he run his whole farm? He said, yeah, he did. And so I said, can you figure out what the entire farm average was? And he did, and it was 4.5 bushel. So now it's worth thinking about, right? You know, a little strip here, a little strip there that wins, that can be an anomaly. But when I start to see farm averages hit this kind of result, that's something to think about. Really, it's not surprising. We think about the original pictures of soil density of emergence, a 1-inch spike. If I can get that right, just like the 100 pounds on every square foot and every seed, does it make sense that we're going to drive 4.5 bushel? It really does. So here's a picture where we ran in rocks. If you don't think it's rocks, watch the closing units on here, and you'll see every once in a while one's going to do a bunny hop. I'm assuming that's not hard soil that's causing that thing to jump up like that, right? That's rocks. And so we challenged it in rocks and did a lot there, a lot of changes in the design as well to overcome those challenges. So in addition to that, the engineers set up some planters here locally that we own, and they tested those planters with half furrow force and half a planter's worth of each one of these wheels in plots that they did here locally. When season hit, they were just like the rest of you guys. They're out in the field with lights, spotlights. They got a pit crew out there ready to change wheels out every pass so that we can compare furrow force against each system out there. Aaron Herman, the R&D agronomist, one of them, he's out there riding the planter, and just like you, he saw rain clouds chasing him as he's out there in the field in between rains. And so this is one of the fields that we planted, or they planted up near Morton. It was Ackerman called the West 70. And it was no-till and marginal. I didn't get up there, but Aaron and Corey told me that it was marginal conditions. I said, well, tell me what marginal conditions is, because that can be defined by everybody. And they said, well, we had to plant around wet holes and ponds in the field. So it was like the rest of us, right? So they went out there, and you see the right-hand side of this picture, the set of closing wheels that they had sitting there ready to change out on each pass. And so then when they planted that field, they let it come up, they let it get to V4, they went out, they did a plant stand evaluation, a yield potential is what they call it, at ear count potential, at V4. And you can see that Force was about a 0.5% lower than the spike and rubber or the dual spike combination. It was an even stand compared to 3 other systems. And then they followed it through to yield. And it was 5.3 bushel average advantage. It was a couple 3 bushel better than the dual spike. And some of those ones that were even at V4 didn't fare so well as it came to yield. And so I would ask you, why is that? What is it here what is it that would cause it to add more yield even though we had the exact same stand at V4? You think maybe it was roots? You think maybe it was better microbial activity, better water movement through that profile to those roots in that plant? It's soil density management. So of the beta growers that ran, one of the beta growers that ran Force was David Hula out in Virginia. And we asked David if he'd be willing to share a testimony or share his experience with us of how he got along with Force this spring. So we're going to play that video next.
This past winter, we had the planter tore down and had opportunities to talk with Precision about some of the new things that they have to go forward, and we volunteered to do the beta testing on the Force. We put 4 rows on. We put one between the transport wheels, and then we put one kind of in the middle where there was no transport wheels on both sides. And then we went out in the field where we were going to just plant some cucumbers this spring, put some corn in a hopper, went out and made a run. Compared to the system that we were currently using, there was a significant difference in that the stage 1 wheels, notch wheels, were just squeezing the soil in where we had the double disc openers just open this trench. The stage 1 wheels closed it up just perfect. And then we had the stage 2 of the stitch wheels, and they left a groove there. They kind of removed some trash, and we liked what we saw. So as opposed to just waiting, we let the corn come up, and then we saw all the corn come up uniformly. I went ahead and changed the other 12 rows. So unlike things that I normally do is change everything one season, I went ahead and changed it all because I was that confident. And this year, we had the absolute best emergence we have ever had. I thought 2018 was good. This was just flat awesome. That was one of the contributing factors, if not the most contributing factor we've had, to where we have surpassed our highest yields ever, and we've been excited about the harvest all season long.
So David Hula broke the world, or world record, national record of corn this last year, 616 bushels. So we've worked with him a little bit in the past on plot cooperators. He's worked with a dealer that we have out in Delaware for the last 20 years. And so he's been a great customer of ours. So anyways, really the conclusion as we have looked at seed, planting seed, whether it's corn, soybeans, as Will talked about, sugar beets, and all the different crops that we've tested, soil density pays. Any questions? Are they available this year? Yes. Yeah, so we have limited commercial release this year. On the rocky areas, we're running a beta rock guard. We did do testing last year, but we feel like we didn't get enough acres. We felt like it worked really well. Didn't get enough acres that we thought this year on rocks we're going to beta. So if you have rocks, let us know. We still have some rows available there. Other than that, on regular ground, we do have some rows left yet. Yes? Is there any... Yep. Is there any soil that it won't cover, super dry clay? Last fall, Australia, what's his name?
David McGavin.
David McGavin, ran it in Australia, and they were extremely dry. And he said without furrow force, he would have never got his corn out of the ground because it was able to pinch it shut, firm it down, and add extra force in some cases, right? Something like that. They was able to germinate his seed. He couldn't believe it. So
to kind of add to that too, when we develop products, we don't just look at them in the U.S.
Right.
So I was in Argentina. We put 1 row of furrow force on a Crucianelli planter in fairly dry conditions. That 1 row that had furrow force on, that corn came up 6 days ahead of all the other rows, and that was pretty dry conditions. So yeah, it'll work well in dry conditions.
Fantastic. Thanks, guys. Appreciate it.
Thank you, guys.